Thanks, Bartek, and to the organisers of this program. Shall we wait 1 minute, as Sally suggests? Then I'll miss the crowd. Yes, lucky I didn't start telling a joke or something. Yes, it's not even 9. Okay, so as I was saying, thank you to Bartek and the organisers of this workshop, and also thanks to the Newton Institute for the entire program. This is joint work with two Chris's, Chris Lustry and Chris Green. At various times we were all at Queensland University of Technology, or QUT, in the city of Brisbane in Australia. But now the Chris's are at Macquarie University in Sydney, which is also in Australia, in case you don't know. And the application here is to flow in a Hele-Shaw cell. So for those of you who don't know, a Hele-Shaw cell is an experimental apparatus made up of two flat plates, normally parallel, held close together, with viscous fluid sandwiched in between them. And the scenario that I'm going to talk about involves a bubble in the cell, sort of translating along the cell. And here is a schematic here, which is taken from a very recent paper by Jack Keeler at the University of Manchester, as well as Alice Thompson and Andrew Hazel. So if you look at the schematic here, this here is meant to be the Hele-Shaw cell like this. So there is fluid here, and then there's a bubble in the cell, and the bubble is sort of moving from left to right, and it's driven by some flow in the far field. Okay, so I am to remember to tell you 4 things about this schematic. One is that if you look at the bubble here in this schematic, it's not convex. It's got 2 kind of tips here, so I'm going to call that a double-tipped bubble. The next thing is that in this actual schematic here, the plates are not parallel. The bottom plate has a kind of a ridge just here, or a rail, or what they call an occlusion, and so the depth of the cell is slightly less in this strip down the centre. The third thing is that there are walls on this cell. This is a good idea if you want to keep your fluid in the cell and not all over the floor. But in the model that I'm going to talk about soon, I'm going to neglect the effects of those walls. And well, the last thing I just wanted to say was that this problem goes back to G.I. Taylor and Philip-Saffman in 1959, and they used conformal mapping to derive an exact solution for a zero surface tension case. And in that exact solution, the bubble is convex, and it doesn't have these 2 tips here. Okay. So, look, there has been many variations of this problem studied over the years. But part of the motivation for our work comes from papers like these from Sally Tanvir and Eckhart Mayberg in the late 1980s. So here Sally has some numerical solutions to steady bubbles moving along a Hele-Shaw cell. And here you can see, what I want you to see here is that this is a bubble with sort of 2 tips, so I call that a double-tipped bubble. This is a half of a bubble. The top half of this bubble, it's a double-tipped bubble. There'd be another half down here. And here are some steady solutions with say, multi-tipped bubbles. And down here, these are numerical solutions to an unsteady version of the problem. The model is actually slightly different there, but you can see the development of some double-tipped bubble in that case. And also there are lots of others, but let me just skip through a sort of very recent example. These figures come from that paper that I mentioned on the first slide from the Manchester group. And I know it's hard to see here. Forget the detail really, but here's some schematic of the types of bubbles that they observe. These are steady moving bubbles in a Hele-Shaw cell. Here are some convex bubbles, double-tipped bubbles, triple-tipped bubbles. There are families of these solutions and so on. These are unsteady simulations where you see some sort of double-tipped bubble emerge, which ends up breaking up into two. In this case here, there's some sort of complicated solution space that I don't want you to worry about. But this here has been drawn for the case where they had that rail on the bottom. So it's slightly different, but putting aside the detail, there are regions of this solution space where there are convex bubbles and double-tipped bubbles and triple-tipped bubbles and so on. They also have some experimental results, and I think you probably cannot see these, but here is a convex bubble and a sort of a double-tipped bubble or triple-tipped bubble. So there is surface tension in all of these. Yes. Okay, so we're interested in these bubbles, the double-tipped, in particular the double-tipped or multi-tipped bubbles. And so the first part of our work was a numerical study in 2017 where we considered this model where there is a steadily moving bubble along a Hele-Shaw cell, but as I suggested before, we're going to neglect the effect of the walls on the cell. So the problem is for a given surface tension value or dimensionless surface tension value to compute the shape of the bubble and the speed of the bubble. In the zero surface tension case, you can write down the solution by hand, and the bubbles are ellipses. The aspect ratio depends on the speed. So for the zero surface tension case, the important thing to note is that the speed is not determined by the solution. It's left as a parameter, and the shape is also not fixed by that solution. But if we include surface tension, we could solve the problem numerically, and I'll just talk about this in a moment. But just to summarize, what happens is that for a fixed surface tension value, there's a discrete number of solutions, and each of these has a different speed and a different shape. And maybe I should just move on a bit. So here, say, this is surface tension, and this is the speed that you get of the bubble. For a fixed surface tension value, there's a sort of a discrete number of these solutions. And for each of these, there's a different u. And in the limit that surface tension goes to 0, each of these branches merge together and select off a particular speed, u is equal to 2 in the limit. And this here is just the same figure, except that there are lots of these branches that we computed numerically. So up here are some numerical solutions to these bubble shapes. And so for example, along this branch, which I would just call the M1 branch, the bubbles look like this, and as we go this way, they become like these double-tipped bubbles that I'm interested in. And the M2 branch, the solutions look like this. There are these triple-tipped bubbles. M3 branch, they look like this with 4 tips and so on. And so there's a very strong evidence that you get two different. So these are different solutions along the branch. So the different colors will be different surface tension values. Okay, so as I'm moving along here, some color scheme chosen by one of the Chris's.
Are all the branches stable?
Well, that is a completely different matter, and the answer is no. They're in this problem, they're all likely to be unstable except for one. But for the problem in an infinite domain, it's not clear whether it's that one or maybe both of these ones. So maybe I will just mention that at the end. Okay, now look, for people who know about these selection problems, that this is they would know that this is completely analogous to the very well-known Saffman-Taylor finger problem and many others. And many people have studied this problem. Even more people have studied this problem. So lots of people know about this. Okay. So let me just tell you a little bit about the way we get these solutions. So the way that the usual model works for Hele-Shaw flow is that you assume that the flow is slow in the cell, and that's a Stokes flow assumption, and you average those equations over the very thin gap between the two plates. Okay, so you assume Stokes flow, and when you do that, here Q is my velocity, you find that the velocity is related to the gradient of the pressure in a form that looks like Darcy's law. So this is one of the many reasons why people study Hele-Shaw flow, is that it is some type of two-dimensional prototype of flow through a porous medium. So here B is the gap. This is all dimensional. This is the only dimensional equation in the talk. Here B is the sort of the depth of the cell, or the gap between the two plates, and mu is the viscosity of the fluid. So if you assume the fluid is incompressible, then together that gives you Laplace's equation for the fluid pressure. Okay, so now this is dimensional, and now from now on everything's dimensionless, and I'll say that phi is the negative dimensionless version of the pressure. Okay, so Q is grad phi. Okay, so phi satisfies Laplace's equation in the flow field, and then there are boundary conditions. There's a dynamic condition on the bubble boundary, and that's just relating pressure to the curvature of the boundary via surface tension. And this is it here. So this is B, is back to my dimensionless surface tension parameter. Here is a kinematic condition which just says that fluid doesn't pass through its own boundary, but it's like a stream function. Let's set it to be 0, and then there is some far field condition. Not sure why Sally uses B for surface tension, but we've done that as well. So what we do then is we map from, say, a unit disk into the flow field. And we've got this complex potential, W of Z, which is analytic because this pair phi, well, this is the velocity potential phi, and psi is the stream function. And really the problem now is to find this mapping. And we can rewrite this problem here in physical space in terms of this complex potential. These are the same boundary conditions. This is the dynamic condition that relates pressure to the curvature on the bubble by surface tension. This is the kinematic condition to say that fluid doesn't pass through its own boundary, and this is the far field condition. Far field in the flow, this is. Okay, so the way that we do this is that, okay, you can write down the zero surface tension solution. It's kind of trivial, and say Taylor and Saffman noted this, and also this is one. I mean, it's sort of a trivial case of one of Darren's studies where there are many bubbles. So as I sort of suggested before, that this zero surface tension solution has the speed u as a parameter in the solution, so it doesn't tell you what the speed is. But for positive surface tension, when b is greater than 0, one way to do this is just to assume that the velocity potential still looks like this, but now write the conformal mapping, the thing that we want to find, as the zero surface tension mapping plus some correction. So now, after all of that, really, I just want to find what this mapping is. And when you sort of plug this into the governing equations, they're all satisfied, except for the dynamic condition, which looks something like this. Okay. So really now the mathematical problem is to find some function that satisfies this condition. This looks a bit hairy, but really it's just the same condition before, which is that pressure is related to the curvature via the surface tension. And this condition is on the unit circle. So if anyone was paying attention to Sally's talk last week, which I wasn't because I wasn't there, I can see on slide 41 there's an equation which looks something similar to this. Okay, so look, I won't talk about this much, but just say that we could solve this problem numerically by just assuming that this mapping, the thing we want to find, we could write it out as a power series truncated. And and satisfied at points around the circle. Okay, so that's just a bit about how to generate those numerical solutions. Now, as I hinted before, many people have studied this problem and variations of this problem. So here is some information about that. So just in terms of the bubbles translating along a Hele-Shaw cell, then as I mentioned before, that I think the first study of that was from Taylor and Saffman. So this is Taylor and Saffman 1959, which is a year after the Saffman-Taylor 1958 paper, which is much more highly cited. So I thought I'd just sort of list people. Here are some people here in this workshop that I know have studied Hele-Shaw problems with bubbles or variations of that, and these are moving boundary problems. So variations of these moving boundary problems for Hele-Shaw cells have been studied by Martin, Ben Ahmad, John Chapman, Darren Crowdy, Linda Cummings, John King, Rob McDonald, Koya, Sakakibara, Michael Siegel, Sally Tanvir, and Zhizhu Ming, and maybe someone else here who I haven't noted. So I just want to give a sense that lots of people have been doing work in this area. But going back just to this problem of a steadily moving bubble, or just say a bubble translating along a Hele-Shaw cell, there's been lots of these studies. In the zero surface tension case, so Darren Crowdy has solved for multiple bubbles. Chris Green and Giovanni Vasconcelos has also done this one for, I think this is for an infinite domain, the wall's infinitely far away, and this one with a channel. There are unsteady solutions with zero surface tension, say, for example, by Rob McDonald, who's here. Now, going back to that selection problem, the one that I described before, even that problem has been considered a number of times. So the selection problem with surface tension, with the channel wall effect, so an even more difficult problem than the one that I want to talk about, was treated in some detail in the 1980s by Sally Tanvir and a number of others. One thing they find is that this is the dimensionless speed u that goes like 2 in the limit that surface tension goes to 0. 2 minus u scales like b to the 2/3 in the limit. And there's some sort of constant here that depends on what family of solutions you're on, what branch you're on. And if you ignore the channel walls, which is what we like to do because it's an easier problem, there's some work on this, and the previous work suggested that the scaling for the velocity u, 2 minus u goes like b squared, which is a different scaling. And that's possible because if you've got channel walls, then taking the limit that they go away, say, infinitely far, doesn't commute with the limit that surface tension goes to 0.
What is M again?
M? Okay, M is going to be just the branch number. So there's going to be a discrete number of solutions, and I'm going to label them 1, 2, 3, 4, 5, and so on. So the constant depends on what branch you're on, different constant for different branch. Okay, so what do we want to do here? We're interested in providing some sort of analytical description of these multi-tipped bubbles. And while we're at it, we want to calculate this constant k for this scaling. And the technique that we're going to use is, or we're going to use techniques in exponential asymptotics to do that. Okay, in green here, just to, again, relate to what's been happening here, if you want to have a look at Sally Tanvir's masterclass, okay, the point here was that you could watch the video, but in fact I think one of the videos didn't work. So anyway, maybe you went to the masterclass, and this subject of exponential asymptotics, I assume, was spoken about in some detail. Okay, so really I just want to pull...
Just for bigger picture, this number of branches, you have 3. Is that just technical limitation? There are perhaps more, or you claim no more branches?
More than 3, sorry?
Yeah.
No, we claim there are infinitely many.
Infinitely. You just study 3, but... Yeah.
Well, I hate doing this thing where people go back all the time, but let me just go back all the time. Here are 3 here, but then here are many more. But I just didn't want to put them on the same figure because it was too messy. So you can't read this, but this says 1, 2, 3, 4. You know what's coming next, don't you? 5, 6, 7, 8, 9, 10.
So basically for arbitrary large
Well, that's almost certainly true, but numerics don't prove that. Okay, now I'll do this thing I don't like doing. Okay, so I'm pausing here just because I think it's a good time to pause. Well, just out of interest, there was a program on exponential asymptotics at the Newton Institute some time ago, which was run by Michael Berry, Chris Howes, Martin Kruskal, and Frank Oliver. So that's of interest. And also, while I'm pausing here, I know that not everyone's interested in Hele-Shaw flows, so if by chance you are not, and you fell asleep or you were not concentrating, from this point, I'm sure you won't remember this, but you could just remember that I'm trying to solve this equation in the box. No. Okay. And again, just to remind you, this is an equation for some f, which is a conformal map, or at least a correction to a conformal map, and it's on the unit circle. So the way we're going to do that is to write out this solution for f in an asymptotic series in powers of the surface tension b in the limit that the surface tension goes to 0. And when you take this thing here and you plug it into that equation from the previous slide, you get some equation for f1, which is the leading order term in this expansion. So without worrying too much about the detail, you can get this f1 on the circle, and then you can then obviously calculate it within the disk. And what's important here for me to note is that, again, this f1, which is the first term in this series of this conformal map, which is a correction, so that we have the zero surface tension map plus f. So we've got the zero surface tension plus f1. It also works for any u. Okay, so again, a u is just a parameter here. It doesn't tell you what the speed is, and also the shape of the thing is still convex, so it doesn't give you any double-tipped or multi-tipped bubbles. And another thing I must say is that this leading order term has singularities, and they're outside of the unit disk. So the unit disk corresponds to the flow field. That's where the fluid is. This leading order term f1 has two singularities outside of the disk. One of them they're both on the imaginary axis. One of them is above the circle, and one of them is below the circle. Okay, so let's say that they're at plus or minus I on q. Q is just some number that depends on the speed u. Okay, so this is important. Okay, so there are only two. And these are like minus 3 on 2 singularities. Okay, so now I want to keep going, and I can continue these equations off the circle. And so let's say I can try to keep calculating higher and higher order terms, but the algebra is very complicated, and as it turns out, we don't need to do that anyway. But because I can't actually write down solutions for f2 and f3 and so on, let me just make a point here by saying that at least near the singularity, what happens is that this leading order term f1 has some behavior near these singularities. There are two of these singularities, if you remember. And the next term has this behavior. So this is like to the minus 3 on 2. This is to the minus 5, and so on. And these powers increase like 7 on 2 each time. The reason that this happens is that we're differentiating twice to get from one term to the next term, and then we're multiplying by some, I think we're multiplying by this, so it should be minus 2, minus 3 on 2, which should be minus 7 on 2, unless I've stuffed that up. Okay, so this repeated differentiation is increasing this power. Now, I haven't shown this here. There are constants out the front, but these constants out the front will also increase like some sort of factorial or 2n factorial or something like that, because every time you differentiate, you bring in this part of the factorial onto the numerator. Okay, so what that means is that, this means that just like almost all singular perturbation problems, the series that I wrote down on the previous slide then must diverge, and you can see that you can kind of see what's happening here from this example where I'm just showing you what happens near the singularities. And the divergence comes because, well, it happens whenever there is a singularity in the leading order term. And when you get these singularities and you have singular perturbation problems, you have to keep differentiating once or twice or whatever to get to the next term. So you keep differentiating, and that is some explanation for why you get this type of divergence. And this type of divergence is called factorial over power divergence. And so you can write that the late terms in the series look something like this. And so this is what we're going to use as an ansatz later. So there's some sort of gamma function of 2n plus something I don't know at this point, divided by some function which we're going to call the singulant, and that's an important function. This function here should be 0 at the singularities, so that we recover this type of singular behavior at the two singularities. This is some prefactor which is not so important, but oh, okay, yes, here. Let's call it the singulant function. I'm not sure who calls this the singulant function, but I know that John Chapman does. And so I will. Okay, so just looking ahead for the moment, what's going to happen is that, okay, what can you do with a divergent series? Well, you have to truncate the series, and the best place to truncate a divergent series is at the least term. So that's called optimal truncation. So we will truncate optimally this series, the one on the previous slide. And the reason we do that is that, well, we have to truncate somewhere, but when we do that, the remainder is exponentially small. And so what happens is that all of the information about our double-tipped bubbles that we're interested in exploring is contained within the remainder term. Okay. And this type of thing happens for other problems where there are, say, one I know about in water waves, where the waves appear in this exponentially small remainder term. And these double and triple and multi-tipped bubbles are kind of like waves. They're kind of like waves on the side of the bubble. Okay. So I think that's all I want to say there. Okay, so just to remind you, I've got some function f here that I'm writing out in this asymptotic series in powers of b. And I'm going to claim that the late order terms look like this, something like this. And now, when you truncate optimally, the smaller b is, the smaller your small parameter is, the further into the series you have to truncate. So the optimal truncation point itself, for say capital N, goes to infinity as little b goes to 0. So to try to determine where you need to truncate optimally, in the limit b goes to 0, you need the terms in the series as n goes to infinity. So it's kind of a bit odd in the sense that maybe we think normally that all of the good information is going to be at the beginning of a series, say the first term or the first and the second term and so on. But here, all of the juicy information is in the late order terms. Okay, so what I want to know is, what are these things here? This is an ansatz, so I want to know what that singulant function is. So if I substitute this ansatz into these governing equations, okay, for a start, the governing equations kind of look like this in the limit that n goes to infinity. Okay, so it's messy. I've tried to grey out some of the detail. All that detail just depends. They're functions of z0, which is the conformal mapping for the zero surface tension case. So some function here. But you can see that for late order, there's this fn that you want to calculate, and you have derivatives of two derivatives on the right-hand side, and here's a derivative plus other terms that I haven't included that are not important in the limit that n goes to infinity. So I'd get this ansatz and I'd chuck it in here, and the first thing that you can find is this singulant function chi. Okay, so this function chi, the one that must be 0 at the singularities, well, let's say that there's one for each of the singularities, must be 0 at the singularity so that this thing has the right singular behavior that I mentioned briefly a couple of slides ago. It turns out that this singulant looks like something like this. Okay, so this is a function of z0, which is written a few slides ago, if you're interested, and that there'll be two of these singulants, one for each associated with each of the two singularities. Let's just call this chi upper, or chi u, and chi l for each of the two. They look the same, except that one of them starts the integral starts from one of the singularities and the other one starts from the other one, so that chi is 0. Each chi is 0 at the appropriate singularity, as it should be. Okay. You can then go to the next order. This is now the next order in n to determine this prefactor f. So without giving you any of the details there, it just looks like something like that. Okay. And then you can also, by matching into each of the singularities, or one of them will do, you can determine this constant gamma, and also, oh, okay, there's another constant here, so that you can work really hard. You have to work harder and harder to get less important information, which is typically what happens. Okay, so you can determine this constant gamma, and you can work this thing out. You have to do it numerically somehow. Okay. So now, as I mentioned before, I want to take this series and truncate optimally. So just to remind you about divergent series, if you look at terms in a divergent series, they start off somewhere and they get smaller as n. This is for fixed b. As n increases, they get smaller, and then after a while, they start to get larger again. So that's why it's good to truncate at the least term. So you take as many terms as you can until you get to this point where the terms start getting larger again. So you truncate about here. Okay. So where is here? So again, I should have a figure for this, but I'm just drawing one now. Okay. So you have terms that are getting smaller, and then all of a sudden they get bigger. So at where the turning point here, the terms are about the same size. Okay. So now, if you think of these two terms being about the same size, one term divided by the next term goes to 1, and this is all in the limit that n goes to infinity. B to the n plus 1 over b to the n is just b. And this thing over that thing, well, I have to look at my ansatz, and it's in a very nice form, the gamma function, you know, that gamma of 2n plus 2 plus another gamma, little gamma, over gamma 2n plus little gamma gives you something like 2n all squared or 4n squared. So what this means is you've got b 4n squared, and you've got a chi squared that you pick up. Must go like 1, or that n goes like chi over 2b to the half. So one of the points here is that if you just truncate a series, the error is normally like the size of the next term, which would be, if I truncate like this, the error, this remainder should be of order b to the capital N. But this is for fixed n. But if I let my truncation point depend on epsilon and truncate optimally, that's when the remainder is exponentially small. Okay, so here, this optimal truncation point n actually depends on b. And when b goes to 0, n goes to infinity. Okay, so now that's telling me where I want to truncate this series. And now I've got some remainder. I'm interested in this remainder, and I'm making a claim that it's going to be exponentially small and containing all this information that I'm after for this particular problem. Okay, you could work this out, but also you could just write it down to say that the remainder looks like something like this. So you could write down an ansatz for the remainder. And this is kind of like a WKB type of thing. It's this prefactor that we already know, e to the minus the singulant that we already know over b to the half. And let's just say it's all multiplied by something out the front that we don't know at this point, some Stokes multiplier. And I want to just think about this function here for the moment. So I'm not sure how I'm going to do this in this much space, but I'm interested in this Stokes multiplier, which is multiplying out the front. And I can substitute all this into the governing equations, but I haven't shown any of the detail. And I can get a differential equation for A. And I can write it in terms of chi. But let's just say in chi space, I write chi as rho e to the I theta. So rho is 0 would be at one of these singularities. And that's good because I want chi to be 0 at the singularity. And I want to write this derivative, the one that I haven't shown here, because I don't want to put in the detail, in terms of this angle theta. So in chi space, chi is some singulant, chi is 0 at one of the singularities. It's like I want to sweep around a bit around one of these singularities at some angle theta. I'm going to take the derivative of this Stokes multiplier in terms of theta and see what happens. So let me try to explain what happens. That this dA d theta, this derivative then, as I'm kind of sweeping around one of these singularities, looks like whatever, but here it is over here. It's some size b to the power of something, e to the minus some stuff over b to the half. So this derivative is exponentially small as we sweep around one of these singularities, except that the stuff turns out to be precisely 0 at one angle, and that angle happens to be theta is 0. So what's happening as we sort of sweep around is that this derivative, which is the derivative of the Stokes multiplier, if you just bear with me, is exponentially small. So this is small. Normally small would be on the front here on the stage, but you can't see here. So this is exponentially small, and then at this special angle, theta is 0, it jumps up to be algebraically small, which is still small, but it's much bigger than exponentially small. And it jumps down again and is exponentially small again. So, okay, this is suggesting that there is some boundary layer in this theta, which I'll talk about in a moment. Okay, so what it's really doing is doing something more smooth than that. So it's telling me this angle theta is a very special angle, and it's now I think about that, it's when chi, the singulant function, is real and positive. So curves on which chi is real and positive we'll call Stokes lines. And it's across these Stokes lines that this Stokes multiplier has a derivative that jumps up and goes back down again. Okay, so because there's some boundary layer in here, I mean, it's obvious that this can't happen discretely. We can write some rescaling. And when we rescale in this problem in terms of some other theta hat, it turns out that dA d theta looks like something like this. So terms cancel, and what you get is that the derivative looks like a bell curve. So really it's like this, like a Gaussian. When you zoom into that boundary layer, it looks like a bell curve. Okay, so when you integrate along, or when you cross over one of the Stokes lines, then you can integrate this and you pick up, or this A increases by a certain amount, and that increase is the integral of that bell curve, which is an error function. And so we get the purple bit multiplied by root 2 pi, which is the integral of that bell curve. That row there ends up cancelling that thing. And the reason it's not root pi is because of that. Okay, so as we cross a Stokes line then, that Stokes multiplier thing, it's taking some value, let's say 0 on one side, and then appears to jump up to some other value on the other side of a Stokes line. But in fact, if you zoom in, it's a smooth but rapid change. And the Stokes lines, just again, is this special angle theta is 0, and that's going to be when chi is real and positive. Okay, so when you step back from that, we know what chi is. It's some function that I wrote down in part on another slide. And so we know where the Stokes lines are for this problem. So let me try to summarize that again. When you truncate optimally, the remainder looks like this. It's like e to the minus chi on root b. And there's some function that we know out the front, and there's some Stokes multiplier that I just discussed in some detail. This chi vanishes at the singularities. I'd mentioned that before. So we have these remainders, and that the size of the Stokes multiplier, the thing in front, depends on where you are in the plane. And in particular, when you cross over a Stokes line, it jumps from some value, let's say 0, up to some other value. And the Stokes lines themselves start at the singularities, and then you can track them numerically, say. Importantly, then, all of this is happening much of this that I've been talking about is happening away from the unit circle. The unit circle is the bubble boundary, but the Stokes line will eventually intersect the bubble boundary. So that means that on the bubble boundary, there are these exponentially small terms that are kind of being switched on across a certain point. And that point is where this singulant intersects the bubble boundary. And then once you get a term like this that you know is switched on the bubble boundary, it's kind of wave-like because it's like e to the minus something or other. So this will have an imaginary part, and that's where we'll get some wave-like behavior on the bubble boundary. Okay, so I think I've just mentioned this here, that the Stokes lines are where the singulant function, the imaginary part of the singulant function is 0, or if it's real and positive. And also, I've already mentioned this, but this small behavior experiences some sort of smooth but rapid change across Stokes lines. And this type of thing is very well known, for example, for Michael Berry and Chris Howes back in 1990. Okay, so putting it all together, I've got an equation like this in the box that I'm going to talk about a little bit. What I didn't say is that you'll get a contribution from each of the two singularities. So do everything that I said twice. You get one of these from one of the singularities and one of these from the other singularity, and that's what the remainder might look like. So it's this, some power law out the front multiplied by some function that we know multiplied by these exponential terms. Okay, so now what I've done is I've rescaled the problem so that this now I'm going to call the Stokes multiplier S. I'm sort of abusing my notation here a bit. So now let's just say that S is the Stokes multiplier, and I'm writing it this way so that it goes from 0 to 1. So I've scaled it so that it's the thing that before it jumps along from 0 and goes up to 1. Okay, before it wasn't 1, but it is now. So what I want to do then is in the next slide is try to explain very loosely about how this works in the plane and how some of these terms can be switched on or not in various regions of the plane. And this is essentially not related to it. It is Stokes phenomenon where it is well known that functions have different asymptotic representations in different parts of the plane. Okay, so here's a figure that I want to talk about. So I just want to use this schematic to try to explain some line of logic here. This is in the plane, and this is the unit circle here in black. So the unit circle, remember, represents the bubble boundary. The fluid is represented by the unit disk. This blue line here is the Stokes line. It starts at that singularity. If you remember, I say that these Stokes lines start at singularities. It starts at singularity above here and whips down here, and in particular intersects the unit circle at some point. There's another Stokes line in green, and it intersects the unit circle at another point. Here these are called anti-Stokes lines, these red ones. I'll just mention these in a moment. Okay, so let's just say what I know is that, or what I'm telling you is that there are some regions here, 1, 2, 3, 4, 5. In region 1, that this exponential that I haven't written down, but both of these exponentials or contributions are exponentially large, and that's because the real part is negative over here. You know, it's e to the minus chi. So I know that these two exponential contributions are exponentially large in region 1, and I can't really have that. I can't have an asymptotic series where these exponential contributions are exponentially large. So I might just assume then that this Stokes multiplier out the front is 0 in both cases. So I'm calling these SU and SL. So let's just say that they're both 0 in this case. Then I'm going to sweep around the plane. So as I sweep around here, I cross this line, which is called an anti-Stokes line. And what happens here is that the real part of chi shifts from being negative to being positive. And so now what that means is that the exponentially large contributions become exponentially small as I go to region 2. But in any event, I'm assuming that they're both multiplied by a Stokes multiplier of 0. But anyway, let's just say they were large and now they're small. now as I cross this Stokes line, one of them gets switched on in a way that I tried to explain before. Okay, so across this Stokes line, one of them gets switched on, and this the Stokes multiplier, the scaled version, will then go from 0 to 1. On this scale, it just switches from 0 to 1, but remember, if I zoomed in, that would be a smooth but rapid change. So in this region 3, then one of these contributions appears and the other one doesn't, but then when I cross the other Stokes line, the second of the contributions, the one from this singularity, is switched on. So now both of these small exponentials are switched on in region 4, and as I cross the anti-Stokes line, they both switch from being exponentially small to exponentially large, and I'm left with these two exponentially large contributions again, and I don't want that. So there's some sort of flaw in that logic, and this is just one of a number of ways of arguing that the only way that all of this could be consistent is if both of these contributions together, added together, precisely cancel each other out. And so this is one way to argue that there must be a solvability condition that comes from getting the two contributions, adding them together, and making that sum precisely 0. Okay. So, I mean, in short, you get this contribution plus that contribution must be equal to 0 exactly. So these two terms here are, I wrote down another slide, but so forget that. But this equation implies that they differ by this discrete number of pi i's, and this is now where I get some discrete m into the equation. I have a formula for these chi's on another slide, and so I can show that this integral then must be equal to 2m plus 1 multiplied by something, and that integral I can do, and it depends on u. So really, just think about this as being a function of u, and here I can see that there are a discrete number of these that depend on m. So I have a number of u's depending on m for each fixed b. And that is what we call our solvability condition. Okay, so another thing you can do, and I'm not showing any details, is take this equation, and in the limit that u goes to 2, you can write down this scaling. And this was one of the things we were after, as I suggested at the beginning of the talk, was this precise scaling, and it looks something like this. Okay, so here are plots of this solvability condition. The blue plots are the numerical solutions that we got a couple of years ago, and now the green ones are just solving this solvability condition numerically. And, well, you can see that the match is quite good, and also that the numerical scheme, for whatever it's worth, wasn't very good when b was too small, and now we can kind of like fill in the gap. Okay, so remember I'm saying that I'm interested in these double and triple tip bubbles and so on.
Can you show again what you fill in the gap? So basically this green part is this symptotic theory, right?
Yes.
And the blue one
is numerical. Numerical result. So the blue part is from a couple of years ago, and the green is the new. I already have numerical solutions for my bubbles. What I want here is some analytical description, but it's of course of interest to compare what you have with the numerical solutions, and I've just done that for the solvability condition here, and I'm claiming that these look very nice because they do. Now I want to compare the bubble shapes, but a problem here is that if I want to actually plot the bubble shape with my methodology, I've got, say, the leading order term, or the mapping from the zero surface tension problem. I might include the first order term f1, but I didn't calculate f2 or f3 or any of the other terms. I skipped over all of those and then truncated, and then I've got an expression for the remainder after optimal truncation, and the smaller b is the further away that truncation point is. So what I'm plotting then is the first term, the map from the zero surface tension problem, skipping all of the terms, even f1, and then just the exponentially small remainder. So this should be a pretty rough comparison, and it is. But it also, on reflection, even just including then this one exponentially small correction term and the very first term gives a pretty reasonable description of the bubble shape. So here are just some of these sort of randomly chosen in this case for different values of the surface tension, which aren't particularly small. And you can see that, I mean, one of these is the coloured one is the asymptotics, and this one here is the numerics. And you can see that in some cases the match is okay, in other cases it doesn't look so great. So for example, just going along one of these branches, M is 2 branch, this is 0 surface tension, we can increase surface tension and the match is not as good, which is not surprising. But as bad as this might look, I would claim that this is actually quite a good match given the constraint that I just tried to explain. Okay. So just one more point, which is on these branches of solutions, the M is 1 branch had 2 tips, M is 2 branch had 3 tips, and so on. At least that was our observation from the numerical solution. Well, here is some explanation, or a summary of the explanation for why that is. This is the mapped plane. Again, this is the unit circle. And this here is the point where the Stokes line intersects the unit circle. And here's the point where the other Stokes line from the other side intersects the unit circle. So we know what chi is at this value here. And we know that the imaginary part of chi is 0 actually here. We know the imaginary part of chi here. We can do that calculation. So we've got kind of a difference between the imaginary part of chi here at the tip and at the Stokes intersection point. And because the thing's going to oscillate, like, you know, we've got e to the oscillating parts, e to the minus I, imaginary part of chi over root b. That distance, or that difference between the imaginary part of that I know from here and here, which is 0, gives you, in effect, the number of wavelengths. So you can do that calculation by hand, and it shows you that, because I know this from some other calculation that I haven't shown before, that the number of wavelengths is precisely m plus a half, where m is your branch number. And so that gives you the number of tips being m plus 1, which is what we expect. So at least I think that's very nice and rather magical. I think John Chapman thinks it's rather obvious. Okay, so for what it's worth, these are the tips here. You can track the tips on these bubbles. One last thing is that this here is the angle that these tips make in the mapped plane, and this here is surface tension. So as surface tension goes to 0, these Stokes intersection points, they become closer together. The wavelengths of these wiggles decreases as b goes to 0, but also the distance between, or from the Stokes intersection point to here also decreases in kind of magically the right rate, so that you retain the precise number of tips on each bubble as you move down the branch. Okay, I think that's enough of that. Okay, so I should summarize this to say these types of selection problems are well known, and so it's not surprising that the problem has a countable set of solutions on branches that I could label 1, 2, and 3, or 0, 1, 2, 3, and so on. Again, just with other selection problems like this, what happens is that if you just write down a perturbation series, your leading order term and any number of correction terms don't give you the discrete branches. And so in what I'm after here, they don't give you the discrete branches, they don't tell you what the speed is, and they don't have any information about double-tipped bubbles or multi-tipped bubbles. The way to do that is to keep going and then take your series and truncate that optimally, well, that's one way of doing that, as I explained. And what I should say really is that this technique that I was summarizing is kind of following John Chapman's methodology. And here are a couple of citations there. And there are, of course, a number of other ways of doing this. So what are we doing here again? We look at the late order terms. This is the important part. Write down an ansatz for the late order terms. It's got the singulant function, which is on the denominator. That must be 0 at singularities of the leading order term of the perturbation expansion. If you want to plot Stokes lines, they're the ones that the imaginary part of chi is equal to 0 because of this explanation that I tried to give you before with this Stokes multiplier of increasing or going through a sharp increase across the Stokes line. That thing happens for all of these types of problems. You truncate the series optimally, and then you go into the plane and try to figure out when these exponentials are switched on and off, as I kind of summarized in my schematic a few slides ago. In this case, for this problem, you've got these two remainder terms that could be switched on and off, but that doesn't seem to work out because you end up with exponentially large terms, and that would cause the whole perturbation expansion to break down. But the resolution to that is to write that down as a selection, as a solvability condition, by making the sum of those two exponential contributions to be precisely equal to 0. Okay, so then you get your solvability condition, and that gives you the relationship between the speed and the surface tension. Also, at the end, I very briefly kind of explained how we can describe the kind of oscillating nature of the tips of the bubbles and show that you should get n+1 tips on the mth branch. Okay, so I'm done now, really, but for me, there's a lot of problems that are of some interest in this area, and in part, I'm interested in this problem that I mentioned very briefly at the beginning, where there was a rail underneath the Hele-Shaw cell. So just to remind you very briefly, a normal Hele-Shaw cell is parallel with two flat plates held close together. At the schematic in the very first slide had a rail or a occlusion or something attached to the bottom. In that case, in variations of that experiment, you can see these double or triple tips bubbles, and they might be stable. But for the case where the plates are parallel, they're likely to be unstable. So I'm interested in this particular geometry where there's a rail, and so future work could involve doing the same sort of thing in that case. But things break, for example, Laplace's equation's not there, and there's no exact solution to the leading order problem, and so on. And so for me, that's a rather challenging problem. So I'll just mention that one, and some others, but which I won't mention. Okay, finally, I'll just sort of say that I should thank the Newton Institute for the support for my visit here and the Simons Foundation. This work was published, the numerical study, a couple of years ago, and just recently the asymptotics part was accepted and is in press. This is my Twitter handle. I noticed that not many people are on Twitter here, but and that's it.
What we recommend at the beginning of the talk technique. Tell a little more about stability of this solution. At least you mentioned at least one of them might be stable out of these branches.
So, okay. For the problem with channel, with walls, I neglected the walls, right? For the problem with walls, the first branch, whatever you want to call it, let's say m is 1, it's those bubbles are likely to be stable, and the rest are unstable. So that's really the answer. Without the walls, it could be that it's the first one or the next one that's stable, but I'm not sure because I haven't done that and done that calculation. And I don't have good evidence, but I mean, this is the wrong type of evidence. But the numerical scheme for calculating steady solutions, which is really not related to time-dependent stability, when you try to find solutions on other branches, you have to really put in a good initial guess because it likes to go to one of them. In this case, it likes to go to the m is 1 branch and not the m is 0 branch.
Talking about what you're talking about stability for small surface tension.
No, I'm talking about time-dependent stability, as in you take one of these.
You increase surface tension, it will not stabilize some?
Okay, let's have room for other people to ask when we have private discussion. Yeah.
I know I've heard it before, but can you remind me why when you truncate optimally you get exponentially small terms?
Okay, so I could have shown you this. So you can do the calculation. That's one answer. And I kind of showed you a bit of this. You can do the calculation by taking the remainder, putting it in your say if you've got an ODE or whatever it is, and it just comes out that it's exponentially small, okay, provided you truncate optimally. Or you can just, as I've done here, just pretend you know that and substitute it in, and you get the prefactor out the front, the Stokes multiplier out the front, and it does what you expect it would do, which makes it consistent with that assumption.
Okay.
It's not that hard.
So you didn't think of trying that?
Yeah, I like the idea, but one of the Chris's didn't want to do that. It's the next one that we didn't bother even trying.
You only did the 0 and
That's right.
infinity, right?
We could have done F1.
0,
It didn't make any difference. We plotted it, but it just still looked.
So then that's surprising they're so far away.
Yes, I think so, yeah. But maybe that was a reason not to include it. I'd have to go and check that, actually.
Okay, let's thank the speaker.
Thanks. Yes, you sure can.
Okay. Can I put it a little lower? Okay. Okay. See if we're working here. Oh. Oh, sorry. I know you have to introduce me.